Okay, now that I'm recording, it should save. Uh,
Okay,
if anything, I'll send you an email after
okay.
class.
All right, so today we're going to do a little bit more on binary search trees. This is probably a really important topic uh, because it leads to a whole bunch of other things, and it gets used in almost any efficient algorithm because it cuts down time complexity a whole lot. So we need to understand this reasonably well. Once we understand these, then we can start to put them into practice. And it would be a good thing to get this understood well before before the the competition. All right, give me just a second. All right, so let's get this started. We talked about this last time when we talked about the overall data structure evolution. So we said that almost any data structure, our three main operations are search, insert, and delete. We want to know how to store things so that we want to know how to insert things into it. We want to know how to look for things. And then we also want to, sometimes we want to know how to get rid of stuff, how to delete stuff. Now, the simplest data structure that we discussed were the linear lists. And there were two ways to implement them. One was using arrays. The problem with arrays was that whenever you needed to insert things, you had to move things around in order to make space for it. And also, whenever you wanted to delete stuff, you needed to make sure that the lost space goes away and doesn't is not seen as a gap in the array, and therefore these array implementations ended up being somewhat inefficient. And so that's why linked lists were invented, so that you could quickly insert and delete things. However, with linked lists, the original advantage with arrays was that when things were sorted, you could quickly do binary search. And with linked lists, these binary search operation simply didn't work. And so therefore, the arrays and linked lists had these pluses and minuses to them. And that's how we end up with what are called as binary search trees. And that's what we're going to discuss today. I think last time we quickly saw these time complexities in these various operations. And we saw that with arrays, especially with sorted arrays, you could do search fast, but then insert and delete was slow. Whereas with linked lists, the search was very slow, but often the insertions and deletions could be speeded up if you look at it the right way. With binary search trees, the fabulous thing was that you could do all the operations reasonably fast. In fact, all the operations were proportional to the height of the tree, and if you could guarantee the height of the tree, then the binary search trees can be extremely efficient. Any questions about this so far before we jump into binary search trees? Okay, I don't see any questions. So let's look at an example of a binary search tree. There's a bunch of terminology that's provided here on this slide, and so let's quickly go over them. A binary search tree starts with the root of the tree, and then it branches and branches, and these branches never come back together. So the tree only diverges starting from the root of the tree. So each of these entities here are called nodes. The nodes carry some values. In fact, they carry something called a key value. And the node that's way at the top of the tree is called the root of the tree. And then there are edges that lead from parent to child. So this is a parent of this node, this is a parent of this node, and so on and so forth. Then there are these other terms that we are using. These two nodes are siblings because they share the same parent. And this piece here is called a subtree because it's a part of the bigger tree. Finally, the nodes at the bottom are called leaf nodes, and the number of nodes that you need to traverse when you start from the root and go all the way to the leaf node is called the height of the tree. So the height of the tree turns out to be very valuable, and you'll see what this means in a few minutes. The important thing with binary search tree is that regardless of which node you look at, what you'll find is that the left child is always smaller than the value stored at the node, and the right child is always larger than the value stored at the node. And you'll see this to be true at every node in the tree. If you look at 65 on this side, you have 63. On this side, you have 67. It's actually a little bit more. You can say a little bit more. It turns out that if you look at the node for 30, the entire left subtree here, all of these nodes that hang off the left child, they're all smaller than 30. And all the nodes that are hanging off the right link, all of them are values that are larger than 30. And this again is true at every node in the tree. If you look at 56, all these values are larger than 56. All these values are smaller than 56. So these are important things to understand about binary search trees. So next we are going to look at how do we search in this tree, and how do we construct these trees, and how do we manipulate them and change them as we go along. One thing that's important to understand is that we are interested in what are called as dynamic data structures, which means that the structure is not static. It's constantly changing, and it changes because we allow insert and delete operations. Because of insert and delete operations, there is constant change in the data structure, and we call all such structures as dynamic data structures. By the way, static data structures are a lot simpler to design because we know they're never going to change. We can somehow figure out how to do this optimally. Whereas with a dynamic binary search tree or with dynamic data structures, you never know how what kind of values are going to come in and what kind of values are going to leave the tree. So it's very difficult to pre-plan and to make the data structure as efficient as possible. Remember, the efficiency of the data structure depends on its height, and that's because we saw this in the earlier slide. What we saw was that the time complexities of all operations on the binary search tree are proportional to its height. It's proportional to big O of h, and so therefore the height is very, very key. And if you can keep the height as small as possible, then your efficiency is going to be quite high. So there's a little more terminology that we need. So let me try and explain those. Each of these, by the way, I told you already that this is called a node of the tree. This is called a node of the tree. This is called another node of the tree, and so on. So each of these entities here is called a node of the tree, and the links between the nodes is called an edge of the tree. If you look at any specific node in the tree, it has these specific parts. The first thing I told you was that it stores a key value. And then I told you that it stores a pointer to the left child and a pointer to the right child. If you want, you could put additional information in these nodes, but that's completely up to you. Regardless of what binary search tree you work with, these three, the first three fields that I mentioned are going to be necessary. So you will always have the key value. You will always have a left child and a right child. So these are going to be nodes in a binary search tree, in every binary search tree. Okay. Now, just to recap what I just said, if you look at a node in the tree, remember the tree is this guy here. So what you see here is that this node here has a key value of 30. It has a pointer to the left child. It has a pointer to the right child, and it doesn't have any other additional information. So key value, left value, right value, and then any additional information that you might want. In typically in many data structures, you might have a pointer to the parent of the node V, and you may have additional information, things like color, the weight of the node. Depending on what it is that you're storing there, you might want to store all sorts of additional information in each of the nodes of the tree. Any questions so far? Okay.
So the height of the tree is determined by the height. The height of the tree is like
More importantly,
measuring the
okay.
like the height of like each key value, right? And then that's how you get the height of the tree.
The height is a concept, as I showed here. You don't go around storing that because you don't know where to store it. Occasionally, you might store it in the root of the tree if you really need it very, very frequently. You can create a new variable or store that separately. But typically, the height is something that you can compute whenever. Pardon me. You can calculate that anytime you want.
Okay, next question. Would the height be equal to 2 or be equal to 3? Because I'm like the root's here, and I'm like 1 here, then that's 2, and that can be 3. That's what that's my.
I don't understand you, Alec. You'll have to speak up.
No, the height of the tree, like the height of the tree. Basically, the end would mean the height of the tree basically will equal to 3, right?
For this tree?
Yes.
Well, it's actually more than that. The height of the tree is how many nodes you traverse as you go down.
Yeah, 1,
from
2,
the root
3. Yes,
to
4,
the leaf.
4.
In this case, it's there are actually 5 nodes you encounter. So really, the height of the tree is 5 in this case.
Okay, there are 5 nodes. Okay,
in some books, they will give it to you as 4, but I prefer to call it 5. Whether it's 4 or 5, it doesn't really matter. It depends on the definition you want to adopt.
Okay.
But
that the key is maybe the key is maybe of the tree. So that means without the key, which would be the roots. In this case, we have to see which one. We have to see the numbers that are larger or smaller than this tree. So that means 30 is smaller. So that means 30 will be on the left, and 70 is bigger. So 70 will be on the right.
Yeah.
And then
correct.
Yeah.
Okay.
Trees.
All right. So let's continue. What do we have next? We have right. So now we're going to talk about how the search happens in the tree. Alec just explained that, so I'm just going to repeat what he just said. So the way you do the search is you start at the root of the tree, and depending on whether the value you're looking for is larger or smaller, you either go left or right. And that's because you know that smaller values are always in the left subtree and larger values are always in the right subtree. So you use that information in order to do your search. So let's say you're searching for 16. Where are you going to go? You're going to start at the root, and then because 16 is smaller than 56, you go left. Because it is smaller than 30, you go left. Because it's smaller than 22, you go left. Because it's larger than 11, you go right. And then you find it, so that's where you're going to stop. So the path that you take in the tree is shown by this thick blue line, and it shows that these are the 5 nodes you're going to visit as you do the search. So that's what happens when you search for the number 16. Is that clear?
Yes.
Yes.
Now, let's say you're searching for 66. What's the path that you're going to take? Can anyone help me?
First, you go right,
All right, then what?
then you go
Give me
left,
the whole path.
and then you go right, and then you go left, and then you're like, oh, 66 isn't here. Or sorry, the last node is a move right.
Where are you going to stop? Give me the numbers.
Wait, okay, 56, 70, 60, 65, 67, return -1 or whatever.
Return 0, or should return null.
That's right. So, so that's where you're going to end, right? 56, 70, 60, 65, 67, and then you fall off the tree. So the height of the tree essentially tells you how many nodes you're going to go and look at, how many comparisons you're going to make before you realize that the value is not in the tree. Any node that's not in the tree might end up making as many comparisons as the height of the tree. So that's really that's the message to understand from this picture and from this example. What I'm going to show you next is the recursive code for binary search tree. This is written in the form of a pseudocode. So if it doesn't look like Java or Python, well, that's intentional. The procedure or this function is called tree search. It takes two parameters. One is the node where you want to start the search and the key value that you're going to look for. So it checks whether the node where you want to start the search is an empty node, is a nil node. If it is, then you just return X. In this case, that X would be nil. It's also possible that the key you're searching for is stored in the node that you just looked at. In that case, again, you're going to return a pointer to this particular node, because that's where either your search ended with success, or that's where your search ended with failure. One of these two will happen. Either way, you're going to return a pointer. It'll be either a pointer to the node where the value is, or it'll be a nil pointer because the node does not exist. So this is a stopping condition for this recursive call or for this recursive function. And this here tells you how the recursion continues. It tells you that if the value you're looking for, which is k, turns out to be smaller than the key stored in this node X, then you're going to do a recursive call on the same procedure, on the same function, tree search, but this time you're going to search for the same value k in the subtree that's rooted at the left child, which means you're going to do the search in the left subtree. And of course, if this is not true, then you're going to do a search in the right subtree. So that's where you will go off. Remember that when you compare the value k with the value that's stored in that node, one of three things can happen. Either the value is smaller, or the value is larger, or the value is equal. If the value is equal, then we will report success. If the value is less, we will continue, but we'll search in the left subtree. If the value is greater, then we're going to continue the search, but in the right subtree. So that's the way this function operates. Very, very simple. It's essentially a three-statement function, and it says, okay, if this is where I want to search, I will compare it with the value stored there. If it's there, then I'm done. If it's not there, either it's going to be smaller or larger. If it's smaller, continue the search in the left subtree. If it's larger, continue the search in the right subtree. So that's the simple function. And this is what we did over here when we searched for 16. We started here. It was smaller than 56, so we went here. It was smaller than 30, so we went here. It was smaller than 22, we went here. But it was larger than 11, so we went right. And then this is where we found, so that's where we're going to stop. Now, what you need to understand here is that is that we want to know what's the time complexity of this search process. The time complexity typically is given by the worst case scenario for the search. And so we start. So in the worst case, we're going to look at we're going to follow the longest path in the tree that starts at the root and ends at some leaf. And we said earlier that the definition of the height of the tree is the longest path starting from the root to a leaf node. And therefore, what we know is that the search process essentially is going to have a time complexity equal to the height of the tree. And what we also know is that this height doesn't have to be log n. It's only going to be log n if you're able to guarantee that. In general, we'll see in a few minutes that we cannot guarantee the height that the height of the tree is bound by log n. That's only in an idealized situation where we've created the tree and maintained it in a nice fashion. If we don't really maintain it, if we allow any insertions and deletions to happen, there's you cannot guarantee the height to be log n for a given binary search tree. Any questions about this? Are you clear about what I just said? Okay. All right, let's move on then. So we're going to do an example. And this slide is simply telling you, it's repeating what I said earlier, namely, in order to search for 66, we're going to follow the red path. But what I'm going to do now is to show you exactly how the recursive calls are going to take place. In the recursive calls, remember, you always start at the root of the tree. So if you go back to this function here, when we first call this recursive function, we're going to set x to be the root of the tree, and we're going to start the search for whatever key value we want. However, if you look at the value 666, and if you start from the root of the tree, you'll see that at least according to the function, it's not equal to 56, but it is not, and it's not smaller than 56. It is larger than 56. So you will follow the right child pointer, and you'll see that that starting with the root of the tree, it goes to the right child of the root. By the way, the root of the tree is the node that contains the number 56. And so I have written it down as at 56 to indicate that it's the node where the root pointer points to. And when the recursive call happens, we're going to go off to the right child of this node. So we're going to go to the right of the node that contains 56. And of course, that node is this number 70, or the node that contains the value 70. And when we compare 70 with 66, we'll see that 66 is smaller. So off we go to the left child of the node that contains 70, and we compare that with 66. So that would be 60. We compare 60 with 66, then it says go right. Then that brings us to 65. And then we go right. And this time we go left. And when we go left, what we see is that the left child of 67 is a nil pointer because there is no left child there. And so when we, if you recall what I said in the code, in the pseudocode, when the node x itself is a nil, if x is nil, then you're going to stop and you're going to return this nil pointer. If you return a nil pointer, we're going to assume that the search failed. If, on the other hand, the return pointer is a real node in the tree, then we'll assume that the search was successful. And what you see here also in this example, when you look at what happened here, you see that in every step we go one node lower in the tree. And so therefore, at every iteration or every recursive call, you may start at the root, but at the next recursive call, you're going to go to one of the children of the root. The next recursive call, you're going to be in one of the children of that node, and so on and so forth. And eventually this has to stop because the height of the tree is fixed, and eventually you'll hit a leaf node. And at that point, either you will find the value or you will stop. So that's the reason why the number of comparisons turns out to be exactly the height of the tree. Any questions?
Nope.
Okay. All right. So now we've taken care of the search operation, and we know that the search operation takes log n time. Next, we're going to talk about the insert operation, and we're going to see how inserts happen in the binary search tree. By the way, many of you may already know all this, but I'm just going to go through it because this is an important topic. And secondly, there are students who have not taken the data structures class, and so it's probably a good idea for you to know how to do this. So how do we go about inserting into this binary search tree? For this particular example, what I'm going to do is to go to a animation. So let's see here. I am going to do a new share. And where did that go? I think it's not this. It's PowerPoint. Oh, here it is. Yeah. Okay. All right. Do you guys see this?
The judge?
Do you still see the PowerPoint slides, or do you see the Chrome
Yes.
browser?
We see
the
BJ's.
Chrome.
You see the slideshow. Okay, so I have to stop the share. Okay.
No, we see
No,
Chrome.
no.
Oh, you
We
see
see
the.
BJudge.
Okay,
Yes.
good. You see that. All right, good. Then that's good. That's excellent. Okay. All right. So I'm going to take you to an animation tool. So to start with, you have an empty binary search tree. You don't see anything on the screen there. So we're going to start to insert items one by one. So let's say we insert the value 10. When we insert, this is the first node in the tree, so it's just going to be a node by itself. That's your binary search tree. It satisfies all the properties that you want, and so everything is well and good. Now let's try and insert the value 12. So the way this works is very simple. It's going to go and search for this item 12, and wherever the point where it fails to find it, that's where it's going to insert the node. And the logic is very simple. It says that, hey, if I'm going to look for 12, I know exactly where I'm going to look for. If at all I want to find it, I want to find it there. So therefore, that's where I'm going to insert it, right? This is sort of the strategy we use at home. We know where we want to find things. We know where we want to find our toothbrush and our books and so on. And so we go and leave it at the place where we think we're going to look for it, right? So that's the idea here. So when I insert 12, where would it go? If my tree were just this 10, I know I would follow the right child. And so that's where it's going to insert it. Clear? So now let's try and insert value 5. And of course, 5 you would search for it in the left child of 10. And so that's where I'm going to insert it. By the way, well, we'll get to that in a minute. So let's say I want to insert 4. Where would that go? Yes?
To the left?
Well, left of what?
Okay. So it will go to 10. It's 4 is less than 10.
So you would start at 10, you would go look at 5, and that's where you will fail. And so it's going to be a left child of 5. Okay.
Yeah.
Then let's insert 20. And of course, 20 is larger than 10. It's larger than 12. And so it's going to hang off the right child of 12. So let's insert 8. 8 is smaller than 10, but it's larger than 5. So it's going to hang off the right child of 5. Right? Let's try 7. Where would 7 go? What node would it hang off? By the way, every node will become a leaf of the tree as you insert it. So where would this hang off?
To the left of 8.
So it would be to the left of 8. That's because it's smaller than 10, larger than 5, smaller than 8, and so that's where it hangs. 15 would be larger than 10, larger than 12, but smaller than 20. So it's going to hang off of here, not here. Okay, make sure you understand that. So, so the red, you can see the red colors showing the path it follows. So let's do just one more. This time, let's do 13. Where would 13 go? Right of 10, right of 12, then?
Left of 20.
Left of 20 and?
Left of 15.
Left of 15. So that's where it hangs. Perfect. So this is your final binary search tree as you insert things. And what you see here is that depending on the order in which I insert stuff, the tree could be crazy, could be very imbalanced. If all the numbers I insert now are larger than 20, this side is going to become very, very heavy. And you're going to have lots and lots of nodes on that side. So the tree may not be very balanced. And that's the problem with binary search trees. It is very dependent on how you insert stuff. So let's go back to our slides. Is everyone clear about how this happens, the insert operation? Okay. So we are going to go back to desktop to, yeah. All right. Are you seeing the slides now?
Yes.
Okay.
Yep.
All right. So we just did this operation, so it should be pretty easy for you. Something happened. Right. So we inserted 10, then we inserted 12, we inserted 5. This is exactly what we followed. Then we inserted 4, 20, and 8, and you saw that tree. And then we inserted 7, 15, and 13, and this is the final tree that we ended up with. And the basic operation is very, very simple. It's written down at the bottom there. You essentially search for the item, and wherever the point of failure, that's where you should insert it. Because you're not going to look for it anywhere else. There's no point in putting it anywhere else, because that's not where you're going to find it. That's not where you're going to look for it. Okay, so that was the insert operation. Now, in order to move forward, we need to understand exactly how to do this. Well, in order to do this, essentially we carry out search like we did before, and then wherever it failed, that's where we are going to hang this new node. So the code also is quite simple. I'll show you that in a minute. Before I do that, let's talk about time complexity. What is the time complexity of the insert operation? Well, what we see here is that the insert operation requires a search process. The search we already know takes not log n time, but the height of the tree. Now, could it be more? Could it be worse than it? Because you are doing some extra work. Well, the extra work is very simple, because the extra work always happens at the leaf of a tree. Wherever we hit the nil node, that's where we're going to hang this new node. And the work it takes to hang this new node is really minimal. It's a constant time operation. And so therefore, the total time complexity of the insert operation will remain as the same as that of the search operation. And so therefore, the time complexity is proportional to the height of the tree. If the height can be made small, it's going to be very efficient. If the height is large, well, it's whatever it costs. Okay, great. So off we go. Here's the code for the insert operation. And even though it looks complicated, it's really quite simple. Let's go over this. It turns out that this part here is, well, of course, we are starting at the root of the tree. That's what this step number 2 says. Let x point to the root of the tree. After that, we are going to essentially do a search, but the search operation is not a recursive operation, but it's a iterative operation. So it's a while loop that says, as long as x is not nil, if the value you're looking for is smaller than the value at the node, make x to be the left child. Otherwise, make x to be the right child and continue with the operation. So this is essentially the search part. However, the problem is the following. If we simply followed search, we would know that we failed only when we hit the nil node. But by that time, we've already jumped off of the node and we've lost track of the previous node where we were. And that's why we need a second pointer to point. That's your pointer y. It keeps track of the parent of x. And that way, even though x falls off the tree and becomes nil, y is still going to be pointing to that parent node. So to start with, x will be the root of the tree and y will be its parent, which is of course nothing, right? So that's your initialization. 1 and 2 are initializations. The while loop going from 3 to 7 is essentially the search operation. That's what I just told you. So until x becomes nil, we keep searching for this item. By the way, if the item is already present, then you could decide to stop and not insert it. So that's an additional thing that you could decide to add to this code at this point. Here we are assuming that anytime you want to insert, you've already done the search, you know it's not in the tree, and you're only inserting it because it's not in the tree. However, if you don't know that it's already in the tree, you may have to modify this code a little bit. Okay. All right. So right now we've understood how to do the search. This is the part that does the insert. So we've come to the search. We know that x is pointing to nil, but y is pointing to the node from which we hit the nil pointer. So therefore, the new node needs to be attached to the node y. So what you'll see here at the bottom is that the new node, which we are just going to call as z, is going to either become a left child of y or the right child of y. Now, it'll be a left child, of course, if its value is smaller. It'll be the right child if the value is larger. So that's what is happening here. And so we have to, so this is the key step. By the way, we are assuming here that what we are inserting is a node. It's not a key value. So the node has already been created. The key value has already been stored. And all we are doing is to insert it at the right place in the tree. Now, the only thing you have to worry about is this statement number 10. Can anyone explain to me what this is doing, number 10? So 10 is executed if y is nil. What does that mean?
That the parent root is null.
Yeah,
So
what
the
does
root,
that mean?
that we don't have a root. We need a root, right?
We don't have a root. If we don't have a root, we don't have a tree. So therefore, the tree is empty. So it's right at the start. If it's right at the start, whatever node you're creating, make that the root of the tree. That's all it says. Okay, very simple. So this whole code is quite simple. It has two parts. You first search, and wherever you fail, that's where you insert it. And the way you are going to insert it is either it might be a left child or a right child, depending on where you failed. And Y, the pointer Y, keeps track of where you failed. So that's all there is to this code. Everyone okay with this? Clear? And the time complexity, of course, is big O of h, where h is the height of the tree. Again, I'm going to go back to my animations and show you some. No, actually, we already did the insert operation. So we're now ready to move on to the delete operation. Before I show you the delete code, let's go back to the animations. Any questions so far? All good?
Yep.
All right, perfect. Are you seeing my browser?
Yes.
Yes, Professor.
Okay, good. So let's do some delete operations. Before we try some things, let me try and explain how this works. There are different kinds of delete operations. Some delete operations are very simple, and some delete operations are not so simple. So a simple delete operation is if it's a leaf of the tree. Let's say we want to delete 4. All I'm going to do is just chop off this link. If I chop this link off, that node falls off, and the rest is still a binary search tree. I don't have to change anything. So if I were to delete 4, it's going to first look for it. Once it finds it, since it's already a leaf of the tree, it's easy to trim this tree. And you'll see that it goes down to that node and just removes it. Very simple. Everyone okay with this? So this is the easiest case. The easiest case is if you're trying to delete a leaf of the tree. All right. Now let's try something a little more complicated. So let's try deleting 15. 15, it turns out, is not a leaf of the tree. However, it's not too complicated because it has only one child. So if I were to remove 15, all I have to do is to take 13 and hang it off of 20, right? Actually, let's not delete 15. Let's try deleting 12. Let's look at 12. 12 also has the same property of 15, namely that it has only one child. It doesn't have the second child, right? If I were to delete this, well, I can, you don't want to lose all of this other stuff. So you need to hang this entire subtree from 10. So what I'm going to do is, since the node I want to delete has only one child, I take that one child and make that the child of the parent of 12. So you will see how this happens. Is everyone clear about what I intend to do here? Any questions?
Yeah. I actually know what he's going to do.
All right. Okay. Just a yes, no is fine. So I'm trying to delete 12, and you'll see that first it locates it. It finds that it has only one child and just makes that child the child of the parent. Is that clear?
Yes.
By the way, if I were to reinsert 12, where would that go?
To the left of 13.
That's right. If I try to reinsert 12, it won't insert it here. It will not go back to that same spot. Instead, it'll get inserted over here. Okay.
What if it had 2 children?
Sorry?
What if it had 2 children? What would happen?
Yeah, that's the next case. Yeah,
Okay.
so let's do that. So before we do that, we have only the root that has 2 children. So let me make this more complex. So let's insert 22, right? Then let's insert 25, and let's insert 21. So now we have a more complicated tree. Now let's try and let's try and delete 20. Now, 20 is not a leaf, so it's not easy to delete. It doesn't have, it has 2 children, so it's not that easy to delete. If I were to delete 20, now there are 2 children, I cannot go and attach both of these to the parent, right? So what do I do? And this is where the problem is. The nodes with 2 children are hard to delete because now we have 2 subtrees and we can't just go and attach both of them to the parent, which already has another child here. This node is not allowed to have 3 children, and so therefore we have to come up with a different solution. So this is where deletes use a nice little trick. Does anyone know what the trick is?
No, but
Okay, that's fine. That's fine. So, so in order to delete 20, what we are going to do is something very simple. We're either going to replace it with a successor of 20 or a predecessor of 20. In this case, I'm not sure what it uses, so we'll have to run this to see it.
Could you put 15 in its place and then put 20 as the right child?
That's right. So the successor of 20 turns out to be 21, which is way down there, and the predecessor of 20 is 15. So in fact, before we delete 20, let's add a few more things here just to make stuff a little more interesting for us. Here I'm adding 16, which of course goes there. Let me also add 18, which will go there. All right. So now deleting 20 is going to be a little more interesting for us. So what is the predecessor of 20 and what is the successor of 20? Can you still see the browser here? Everything is okay?
Yes, we can
Okay.
see it.
All right. So what is the successor of 20 and what is the predecessor of 20?
Mm, 15, like.
Successor doesn't mean child.
Well, now it would be like
Successor means in the sorted order, what
Oh.
follows it and what precedes it.
19 then.
Well, 18.
Oh, yes, you're right. Yeah, okay.
In the tree, it's not anywhere else.
Yeah.
So in the tree, the predecessor is 18, and in the tree, the successor is 21. Clear?
Yes.
What is the predecessor of 8? The predecessor of 8 would be 7, and the successor of 8 is actually 10, right?
Yes.
Give me just a minute. My computer is running out of power. Let me get my power cord. Okay, sorry about that. All right, so what we're going to do, as I said, is to either replace 20 by its predecessor or by its successor. So in this case, we're going to either replace 20 by 18 or with 21. If, let's say, I took 21 and I moved it here, would this tree still be a binary search tree? That's the question. And what you'll see is that if I were to put 21 there, everything on the right subtree is still larger than 21. Everything on the left subtree is still smaller than 21. And so therefore, everything should be good. Is that clear? So our goal is to somehow remove 20, but make sure that the tree we are left with is a binary search tree. And so let's see what this does. It goes and finds 20, then finds a predecessor and moves it up there. And now, as you can see, 20 has gone away, and 18, which used to hang here, is now moved over there. Is that clear?
Yes.
All right. So what happens if I were to delete 18? What would happen?
It will move 16 up there.
Because, yeah, that's right. So predecessor of 18 is 16, and it would find 16 and put it up there. Okay, so we could try that. 18, and boom, it goes find 16 and replaces it and gets rid of 16. Now, it was convenient because 16 was a leaf and it could easily cut that off. The problem is, what if the predecessor is not a leaf? Would it still work? All right. Now let's look for predecessors in the tree. And what we will see is that predecessors always are either leaves of the tree or they have only one child. So for 16, the predecessor is 15, but it has only one child. 22, the predecessor is 21. It's a leaf of the tree. 8, predecessor is 7. It has 7 is a leaf of the tree. What about 10? What's the predecessor?
8.
It's 8, and again, 8 has only one child. Now we already know how to delete a node with only one child. And so, by the way, if I were to remove 8, what happens? 7 simply hangs off of 5. And so if I were to delete 10 now, what will happen is that it will go find its predecessor and then replace that with 8, and then remove this node by simply hanging this off of 5. And you'll see that that's exactly what happens. It finds 8, replaces it there, and simply removes the node. Everyone okay with this?
Yep.
So it's quite a bit more complicated, but what you'll see is that in terms of coding, it's actually quite manageable because we just need to understand what the pieces are. Now, the next question is, how the heck am I going to find the predecessor of a node? And this is where it gets a little more interesting. So let me insert a few more values just so that the problem becomes interesting for us.
Would you look for the value you want to delete and then keep looking for the smaller one?
Can you repeat that?
So would you look first for the value you're trying to delete and then look for the smaller ones to find the closest predecessor?
Well, what does it mean to look for smaller one? That's not clear.
Yeah, so say you want to delete 16, right? So you do
Yeah.
a binary search, you find 16, and then you keep looking to the left to find a predecessor.
Right. So that's actually roughly correct. So give me just a minute. Let me add a few more things so that the problem becomes more interesting for us. Yeah. Okay. So if I want to find the predecessor of a node, first of all, I know it must be in the left subtree, right? Because predecessor values are smaller. So if I want the predecessor of 8, it has to be in the left subtree. Now, in the left subtree, every value is smaller than 8. But how do you define the predecessor? It's actually the largest among all the values that are smaller, right? So how do I find the largest in this subtree? In order to find the largest in this subtree, I start at the root of that subtree and I keep going right. And if I cannot go any further right, that value must be the largest in that subtree. So therefore, if I want the predecessor of 8, I go to the left subtree. That's everything over here. And then starting from here, I only go right as far as I can go. And that would be my predecessor. If I want the predecessor of 16, I would go to the left child and then follow the right pointer as far as I can go. Since it has no children, this must be the predecessor. All right. So predecessors are easy to find. For instance, let's say, what's the predecessor of 5? I go to the left child and then I follow right pointers as far as I can go. So that must be 4. What is the predecessor of 4? I go to the left child, then follow right pointers as far as I can go. And that would be number 3. So things of this sort. So that's really what our predecessor pointer is. So now we are ready to look at the code that we need for the pseudocode that we need. So let me jump back to our pseudocode. Everyone see the slides now?
Yes, Professor.
Okay, so here's your delete code. And give me just a minute. Let me close some of these other things. Yeah. Oops, sorry. Okay. So again, if I want to delete some value, so let's say here I want to delete in this tree a node called Z. So in order to do this deletion, first I have to search for it. So I will first do the search. Then once I locate the node, I will check whether it has 1 child or 2 children, and then based on that, I will do further operations. So what you'll see is the following here. Oh, by the way, because we are given the node itself, we've already done the search, so we know exactly where it is in the tree. So now, then the only thing I'm left with is to find the predecessor. By the way, this code is written with successor, so it's essentially the same code, but you have to flip the comparisons. But I'll explain that to you. So essentially, if I want these, so I've already located the node. I know that it has 2 children, so I'm not able to delete it directly. So I have to first replace it with either the predecessor or the successor, and then move forward. So the first thing I do is to find the successor. So if both the left child, if either the left child or the right child is a nil pointer, then I know for sure that the node Z has at most 1 child. And in that case, things are easy to, those are the easy cases. If it's not, then so if it is, then I'm going to do something. Otherwise, I'm going to find the successor, and then I'm going to do the replacement. So Y is the node that needs to be deleted from the tree, and I'm going to make sure that Y is a node that has at most 1 child. So so either Y is going to be Z itself, or it's going to be a successor of Z. Either way, we know for sure that it has at most 1 child. Now, I'm going to then check whether the left pointer is nil. If the left pointer is nil, it's the left child that's missing. Otherwise, it's the right child that's missing. Remember, Y has at most 1 child. So here we are trying to figure out, is it missing the left child or is it missing the right child? Or maybe it's missing both, but that's okay. So if it's missing the left child, then X will be if left of Y is not nil, X is the non-missing child. Otherwise, X is the right child. what happens next? Well, here we know for sure that y has only one child, and we want to delete y. But in order to delete y, we need the parent of y, and that's the node x. And then we're going to fix the parent pointers of the. So then we are going to remember it's the node y that we have to remove, and so we're going to make connect the child of y to the parent of y. So that's what this says. If y is a left child of its parent, then make x the left child of the parent. Otherwise, make x the right child of the parent. So it's trying to figure out where we are going to hang this entire subtree. And finally, we do the one last part, which is to copy the node that we just deleted. We're going to copy it to the node that needs to go away. In this case, z is the one that needs to go away. So the key value of z becomes the key value of y, which is the node that we ended up deleting from the tree. Okay, so I understand that this is a little bit more complicated. If you followed it, great. If you didn't follow it, well, you can still use this code. All this code is available both in Python and in Java. So all you have to do is to call the right functions and use it in your code. I'm just explaining this to you because it's really, really useful to understand how the delete operation works. Same with the insert. It's actually even more important to understand how the insert operation works. As we move on to the next topic, you'll see that this is actually quite significant, and it's quite important. Again, it's very easy to convince yourself that the time complexity is big O of h, where h is the height of the tree. All right. So before I talk about balanced binary search trees, are there any questions? I would definitely recommend that you go to the animation websites and play around with it a little bit more. Okay. For instance, try out what happens if I insert the numbers 1, 2, 3, 4, 5, 6, 7, all the way up to 10 in that order. Okay. Or try other orders and see how the tree changes. And in each case, make sure that what you get is a binary search tree. All right. But you'll see that the tree looks very strange depending on what order you insert things. All right. Also, if you throw in inserts and deletes randomly, then the tree might be nice to start with, but as time goes on, it could get very skewed and very imbalanced. And an imbalanced tree may have a very large height, and if it has a large height, what happens? All the operations become inefficient. And so therefore, it's really the next topic is quite important in the sense that we want to know how to keep a binary search tree to be as balanced as possible. It turns out that many people have worked this out. There are different kinds of balanced binary search trees. For instance, there's something called the AVL trees. There's something called the 2-3 trees, and something called red-black trees. There are many other things in the literature, but these are the three that you will find in your textbooks often. AVL trees were invented by these three Russians, Adelson, well, even I can't remember their names anymore, but they showed how you can take any binary search tree and balance it perfectly. And they showed that as you insert things, it doesn't matter in what order you insert them, you can still keep it perfectly balanced. So every time you kind of make some operations and you balance things out. 2-3 trees were yet another invention where they said, okay, let's not be strict about binary trees. Let's allow nodes to have either, some nodes could even go up to 3 children, and that's okay. And it turns out that balancing is a lot easier if you have 2-3 trees. And from the concept of 2-3 trees came the concept of red-black trees, which in the end, most people agree are the best balanced binary search tree implementations you can get. In a red-black tree, the procedures are very efficient. The main difference is going to be that it's a binary search tree, but each node will have colors. Every node will either be a red node or a black node. All the operations are quite efficient, but more importantly, insert and delete operations are super efficient. In fact, they're more efficient than in a binary search tree. And we do something called lazy balancing, which means, like most of us, we don't do the work unless it becomes really, really necessary. So it waits until things get really bad, and then it fixes stuff. And that's why it's called lazy balancing. What the red-black trees guarantee is that the height of the tree is at most 2 times log n. It doesn't guarantee log n, which is the best possible height, but it says, okay, I'm a little lazy, but I will still guarantee you 2 log n. And so therefore, all your time complexities are going to be at most 2 log n, which is still big O of log n. So it's still very efficient for search, but more importantly, it's very efficient for insert and delete because it doesn't go around balancing every time you insert. With regular AVL trees, what happens is that I could design a series of operations where I insert something and it goes and does a lot of work and balances things out, and then I delete it, and again it undoes all the work that it did. And so I can keep inserting and deleting, and it'll end up doing a heck of a lot of work. Whereas these lazy red-black trees, it'll just insert and delete very quickly, and it will the operations will be very fast. So laziness, it turns out, sometimes is helpful for us because we don't end up doing extra work. And most of us know this. We don't necessarily go and jump and do things immediately as is needed. We wait for stuff, and sometimes work takes care of itself. That's what the red-black trees do as well. Here's an example of a red-black tree. What you'll see is that the first thing you should notice is that it's already a binary search tree, in the sense that at every node, values to its left are smaller, values to the right are larger. What you also should notice is that every node is either a black node or a red node. Furthermore, you'll see that the root is going to be always black. The leaves of the tree are always black. And by the way, the leaves of the tree are essentially the nil nodes. This is where you will go when you can't find anything. So they're always going to be black. The important property are the last two, that says that the red nodes are never next to each other. Okay, you will never see a red node having a parent-child relationship. They may be siblings, but they are never connected to each other by an edge. And finally, the most important one, which says that the black height is exactly the same. What does that mean? It means that if you start at the root of the tree, and if you end up in any leaf, it doesn't matter which leaf, the number of black nodes you will encounter is always exactly the same. Okay, so let's look at one example here. If I go this path, here is one black node, and I hit the leaf. So that's 2. I could go from here this way, and even here, I encounter only 2 black nodes. I could go here, and I only encounter 2 black nodes. I could go here and turn this way, and I still only encounter 2 black nodes. So it doesn't matter which path I take, I will always encounter the same number of black nodes. Now, red nodes, since they are never in succession, it might be that as I traverse this, every alternate one is red, but the number of black nodes is going to be fixed. Once I do the tree, the number of black nodes that I will encounter on any path is exactly the same. The number of red nodes, we know every alternate one could be red because they cannot be touching each other. So, so every black node might be separated by a red node. So therefore, the height of the tree turns out to be at most 2 log n, but you're never going to, it's never going to be worse than that. So it turns out that, you know, if you maintain these red-black trees, things are going to be great for you. They're going to be very efficient. Inserts, deletes, searches, all these operations are going to be very fast. In fact, your height is always 2 log n at most. And so therefore you can do search, insert, and delete in big O of log n. I'm sort of out of time today, so I won't be able to tell you exactly how to do inserts and deletes with red-black trees, but you could go to the animation sites and play with them yourself. This is an entire lecture in itself, and I'm not sure I want to spend the time. You should know how to use this code. And if you feel really brave, you can go and read up on red-black trees and understand how they work. But you should definitely know how to code with them. And remember, the best thing about binary search trees, about balanced binary search trees, is that all these operations, search, insert, and delete, are very fast. So any situation where you have to keep track of a set of values that are constantly changing, things are being inserted, deleted, and so on, this is the best data structure you will have. Okay, so if somebody tells you, hey, here's a set of values, I may add a few things here and there, I may delete a few things here and there, and occasionally I'll ask you to search. Well, you should immediately think of binary search trees, or actually balanced binary search trees. And in particular, you should think of red-black trees, and there's ready-made code. You just have to go and use them. So you store your data in a red-black tree, and it'll allow you for very fast operations of insert, search, and delete. It's way better than arrays, because in an array, I can search in log n, but I can't insert or delete in log n. Here I can do that. It's better than linked lists, because in a linked list, I cannot search in log n. Here I can search in log n. So red-black trees is gives you the best of both worlds. It allows for search as well as insert and delete in log n time. So all we are left with now is to go and figure out how to use them in a program. And they're already available to you in Java and in Python and in C++. So jump right in and use them. Cool? Any questions? So let me end the show here.
I have a question. It's kind of related because for this week's competition, there was a problem about binary search. And I got a time limit. I thought like I was, I thought it was the best solution, but I wonder if that's because I use Python instead of C++, that the time limit.
It shouldn't be. Did you balance binary search trees, or did you use regular binary search trees?
Regular. So,
see, regular can become a problem if the tree is imbalanced. So just go and replace your regular with the red-black tree, and it should magically go faster.
Okay, perfect. Thank you so much.
Anyone else? So let me stop the share and let me look at your faces and see if you have any questions. Today, not enough chat. What happened? Is all clear?
I know where she was. Yes. I just walked on the site, it was very.
Thank you, Professor.
Okay.
I'm prepping right now. I'm preparing for our interview, so that's one reason why.
All right. Thank you, Alec. Yeah.
You're welcome.
Okay. Enjoy the Saturday session. I'll have a competition for you.
Thank you. Have a good weekend.
Ciao.
Bye. Thank you.
Bye.
Thank you, Professor.